Good morning. This is our first online lecture. I am sitting in our usual lecture hall, but just in case there is an error with the lecture recording, I'm also recording this lecture on my own laptop. I'll be posting slides to Moodle as well as a video recording. Today's lecture is based on lectures 14 and 15 in the total notes, which cover cipher systems and RSA encryption in particular. And then we'll be getting into material from lecture 9, which is the Chinese remainder problem. That's a lecture we haven't spoken about yet, but it will be important for RSA. So the basic layout of this lecture is I'll be talking about some additional ciphering systems and then get to the RSA encryption in particular. And I'll close the lecture talking about the Chinese remainder theorem and show some problems that we can solve using it. So remember that when we're talking about a crypto system, our core idea is that we have some message that we want to send. We call that the plain text because that is human readable. If I could just give you a sentence, you can read it. Our encryption system is going to turn this into some other kind of message that is just complete nonsense to an outside observer. We call this the ciphertext. And even though we have a single idea for this method of encryption, we'll have some set of keys that we're using to encrypt by. You can think of each key as locking and unlocking the message. You need to have the correct key to go from the ciphertext back to the plain text. So mathematically, I'd say that for each of my keys in the set K, I have some encryption function f sub k. It takes me from the set of all possible plain texts, and for each one of those, I'll have some ciphertext. The cipher I talked about previously is one of the simplest ciphers. It's called the Caesar cipher. In the Caesar cipher, we're going to be scrambling letters of the alphabet. So the plain text, what are all the possible messages I could send, just consists of the alphabet, A, B, C, and the rest. And the ciphertext also consists of the alphabet. We're just changing letters into letters. The idea was just for any integer k, we can move the letters of the alphabet over by k places and wrap around at z. So this is similar to the idea of modular arithmetic. For example, let's shift the alphabet over by 5 places. My message that I want to encrypt is Klaatu Barata Nikto. It's just a nonsense phrase from a very old movie. And I'm going to take each of my letters and move it over 5 places in the alphabet. So I get this new phrase, and I'm not going to bother pronouncing that. A very simple idea. You can try this out for yourself. There's a website called rot13.com. Feel free to play around with the Caesar cipher. You can encrypt and decrypt any messages you like using that online tool. Now, the Caesar cipher is historically important. It was used in Roman times, but with modern computing power, it's no longer an effective way to hide messages. Since there's only 26 characters in the alphabet, there's only really 26 possible Caesar ciphers. Either I've moved over by 1, or moved over by 2, or moved over by 3, and so on. If I move around by 27 places in the alphabet, since there are only 26 letters, that's the same as moving over by 1 place. So it might not be fun to do this by hand, but you could just have a computer try out all of the Caesar ciphers, take less than a second, and from those you'll get the decrypted message and 25 other pieces of nonsense. So in modern times, this is a trivial cipher to solve. You would never use this if someone's life was on the line or to save a bank password, anything like that. Since we're already using the idea of wrapping around the alphabet, let's go ahead and commit fully to the idea that I can use the integers mod 26 for encryption. So I'm going to make an assignment and say that the letter A is the 0th letter of the alphabet, the letter B is the first letter of the alphabet, and so on, up to Z, which is then the 25th letter of the alphabet. If you prefer, you can really have A, B1, B2, and so on. I'm sticking with how it's laid out in the total notes, so you can follow along with that. Now that I can treat my letters as numbers, what can I bring to this system using the things we've learned about from modular arithmetic in the past weeks of this course? What can we do in Z mod 26Z? So one example of a cipher based on modular arithmetic is the affine shift cipher. So I'm still in the business of changing letters into other letters. Although now I'm thinking of my letters really as residues modulo 26. So for this cipher, my set of all possible plain text messages and my set of all possible ciphertext messages are both equal to the set of all remainders mod 26. I want to apply a formula to my plain text. So here, X is going to be some residue, mod 26, that's really standing for a letter, right? If I say X is 3, 3 is one of my residues, mod 26, and 3 would correspond to the letter D of the alphabet. I'm going to apply the formula AX plus B, and whatever I get from this calculation, mod 26, is going to be my ciphertext. So this is the formula I'm using to scramble the alphabet. I'm thinking of them just as residues mod 26. And I have two free parameters I can play around with. So A and B are going to just be integers, or residues mod 26. And B can be any integer, but at the end of the day, I still want to be able to decrypt my message. We've seen that multiplying can be tricky, particularly since I already know that 26 is a composite number. So I'd better be sure to pick an A that does have a multiplicative inverse. So A had better belong to the set Z mod 26Z cross, or as I like to call it, A had better belong to the group of units mod 26. All I'm asking for is A should have GCD of A and 26 be equal to 1. Those should be relatively prime. So 4 different ways to say the same thing. Our decryption formula is going to be right here. If Y is my ciphertext, Y is the letter that has already been scrambled, in order to recover my original letter, my original residue mod 26, first I'm going to subtract off B, and then I multiply by the inverse of A. So again, B can be anything. I can always subtract by B. A has to be one of these special numbers that has a multiplicative inverse. If I keep that same message, Klaatu Barada Nikto, I need to go ahead and pick my parameters. So I've chosen A is equal to 3, B is equal to 7. And my first step is to change each of my letters here into the corresponding number, the corresponding remainder mod 26. So K becomes 10, L becomes 11, my A's become 0, my T becomes a 19, and so on. This isn't encrypted yet, it's just a different way of thinking about the alphabet. And in each different letter, I'm going to apply the formula 3, which is my A, times my letter, plus 7 gives me the encrypted letter, gives me my cipher. So my 10 becomes an 11, which is saying that the K will become an L. My 11 becomes a 14, which, I can already see my 14 is becoming an O. My A, which was a 0, becomes a 7, and so on. So I'm just using a simple formula for modular arithmetic. In terms of the plain text and the ciphertext and the keys, this formula is determined by 2 different numbers, my A and my B. So each of my keys is actually a pair. It's just telling me what are the fixed numbers in my formula. So before, for the Caesar cipher, I had 26 different keys, which is not really a whole lot of keys. For this kind of cipher, how many keys do I get? I said already that B can be any of the residues mod 26. A has to be one of the residues mod 26, which does have a multiplicative inverse. And how many of those are there? That's determined by the phi function. And I calculate phi of 26 is equal to 12. Again, that's because 26 factors as 2 times 13. So I multiply 2 take 1 times 13 take 1, I get 12. So with 12 choices for A and 26 choices for B, there will be 312 different keys I can have for the affine shift cipher, at least the affine shift cipher on individual letters. So that's more than the Caesar cipher, but still not so many that we can stop a brute force attack. So what do I mean by that? 312 tests to try and see which of them gives you a reasonable plain text message. This is still something that a computer can do in the blink of an eye. So you can use this to confuse your friends and keep people out of your personal diary, but I would not trust the affine shift cipher to keep anything secure against someone with a computer, for example. Now, there's only so far we can get by substituting individual letters out for other individual letters. The key idea here is that we want to take a message that we have and find a way to treat that message as a number so we can then use tools for modular arithmetic. Fortunately for us, in modern days, basically all information is just numbers. So let's say that you have some data file that consists of 50 bytes. That's not a terribly large file by any standards these days, maybe a text or a tweet. But that file will consist of 400 ones and zeros, since 1 byte is 8 bits, and every bit is either a 0 or a 1. So if we do have 400 ones and zeros that specify some piece of information, we can turn that into an integer by saying those are the base 2 digits of some number that I'll call capital P, again for plain text. If B399 is the top bit, I'll multiply either a 0 or 1. I'll multiply that by 2 to the power 399. Then I'll take the next bit, B398, multiply that onto 2 to the power 398, and so on. My B sub 1, I multiply by 2 to the power 1, and my smallest bit, my B0, gets multiplied by 2 to the power 0, and this will give me some integer between 0 and 2 to the power 400. And as I'm looking at my slide, this should be strict less than. So how big is that? Roughly 2.5 times 10 to the power 120. We're talking about some integer with 120 digits. Again, that feels like a lot for the kinds of calculations that we do on a day-to-day basis, but for computers working with numbers, this is basically no problem at all. So how can I use a message that is really a very large integer in modular arithmetic? I just need to pick a modulus, capital N, that's bigger than 2.5 times 10 to the 120. I'll have a little bit extra room, but I can fit every possible message of this size into the integers mod n. And the cool thing about it is that even though this number is very large by day-to-day standards, the integers modulo n still behave according to all of the rules that we have discussed this term, and we can use all of the techniques that we've discussed so far in this modular arithmetic system. So what are we going to do with this message? How are we going to encrypt it? Yes. So we're treating our plain text messages as some integer modulo n. N is some very large number. And the ciphertext that we get is also going to be some residue mod n. So this is exactly like the affine cipher that I just talked about, only the numbers will be a little bit bigger. And we want n to be big enough that an attacker can't just try all the possible ciphers. So ideally, we would want hundreds of millions of different possibilities, so that you can't just roll through all of them and see what you get. If you are worried that you have more information to send than just 50 bytes, one of the possibilities is we can just take a bigger n. The only thing there that's holding us back is computation time. Or you could break up your message into smaller 50-byte pieces, the same way as I take a whole sentence and only encrypt the individual letters. So I could break, say, a 1 megabyte file down into 50-byte pieces and encrypt each of those separately. So how does RSA encryption work? We're going to take a page out of Diffie and Hellman, and we're going to use exponents modulo n. So if p is our plain text, again, this is just some very large integer, the digits in base 2 that represent p are exactly the bits that represent some piece of digital information. The ciphertext that we're going to get is going to be p raised to some power e. So it's just exponentiation. We still want to be able to decrypt. So if p to the power e, e for encryption, gives me the ciphertext, I want c to the power d, d for decrypt, to give me back the decrypted message. Now, we saw in the affine cipher, you need to be careful about which multipliers, A, will actually work for this. So here, we need to be careful about which exponents, E and D, will actually allow us to decrypt. If I put those two equations together, p to the power E is my ciphertext, and raising it to the power D is supposed to get me the original plain text back. But that's also the same as p to the power E times D. I want this equation to work, so thinking about exponents modulo some integer n, I know that my plain text raised to the power phi of n is congruent to 1 modulo n. So that means, and I see a typo on this slide, I apologize. That means that E times D is going to be 1, and here's my error, it's going to be 1 modulo phi of n. So phi of n is the special number that governs exponents modulo n. E times D had better be equal to 1 modulo phi of n. So that tells me that E has to have a multiplicative inverse modulo phi of n. So E is going to be a unit mod phi of n. And E must belong to the integers mod phi of n, which have multiplicative inverse. So z mod phi of n z cross. Or really, this is just asking E must have GC, the greatest common divisor of E and now phi of n be equal to 1. So this is the RSA encryption system. My plain text and my ciphertexts, these are just integers mod nz, and ideally we would like n to be as large as possible. My keys, my set of keys is just the units modulo phi of n. So again, these are just the remainders which have no common prime factors with phi of n, whatever phi of n turns out to be. My encryption says, take your plain text, this is just a number, raise it to the power e. My decryption says, this is my ciphertext, to decrypt, raise it to the power d. And of course, these are taken modulo n. Now, you might have some issues. I have skipped a couple holes that I need to fill in now. I only know this exponent law for certain integers. I claimed that I can say the plain text to the power phi of n is 1, but that only actually works if p and n are relatively prime. So what could go wrong if the message I want to send turns out to be a number who has a common factor with n? That is potentially a problem with this system. And secondly, how are we going to calculate phi of n for some 100-digit number or 1,000-digit number n in the first place? So to make things easier for ourselves, we're going to assume that n has a very special factorization. So p, lowercase p, and q are going to be two different and large prime numbers, and n, I say, is going to have the factorization p times q. This is really nice because we can calculate phi of n very easily, since we are the ones who picked the prime factors. I know that if I have two distinct prime factors, that phi of n is just prime factor number 1, take 1, times prime factor number 2, take 1. So p take 1 times q take 1. But that's something special that we know and adversaries don't. If you don't know the factorization of this number, you don't get to use this formula. You will have to calculate out all of the residues mod n and check them one by one, or so I claim. We'll get back to that on tomorrow's lecture. So if we have some n, which is the product of two prime numbers, there's only 4 possibilities for calculating the GCD of the message we want to send, and n, because n only has 4 divisors. So the GCD could be 1. The GCD could be just a single one of the prime factors. The GCD could be the other prime factor, or the GCD could be n. So if we're in the first case, that means that the message p is relatively prime to n, and we already know that the phi of n exponent trick will work. That is a theorem that we already proved. If the GCD of p and n is n, that means that the message I want to send is 0 mod n. And since 0 to any exponent is still 0, I guess that means that I cannot send 0 as a message. So there's a single message in this space that I cannot actually encrypt this way. So we can just promise to ignore that 1 and never attempt to send 0. The interesting thing that happens is what happens if the GCD of p, the message, and n is one of the prime factors. So in this case, the prime, lowercase p, is a divisor of the message we want to send, our plain text, capital P. But q is not a prime divisor of p. That means that the GCD of p and q is 1. Let's see what happens when we raise our message p to the power e times d. So again, we picked E times D so that E times D is 1 modulo phi of n. E times D is actually the integer k times phi of n plus 1 for some integer k. What we want is that the message raised to this power should come back to exactly capital P again. So capital P to the power E will be some ciphertext, capital P to the power E, and then to the power D should recover the plain text message. That is our decryption. So this would be very easy to solve if we could work modulo the two different primes separately. The easiest would be just working mod P. That is one of the prime divisors of our message. So my message that I want to send reduces to 0 modulo this prime. 0 modulo any power is still 0, but 0 is also congruent to P, modulo P. So I get what I want modulo this common prime divisor. What happens for the other prime divisor? If I have the message that I want to the power k times phi of n plus 1, I'm looking modulo q, I want to get back to the original plain text message P. So what I'm going to do is say, in this exponent, I have k times phi of n plus 1 copies of the plain text. So I'll pull out 1 copy of the plain text here, and here is the rest of those copies of the plain text. And I've used the formula for phi of n. The k is staying the same, but phi of n is p take 1 times q take 1. Let me rearrange the formula to bring in the exponent q take 1. So I have p to the power q take 1, and then raised to this other power, and 1 extra copy of p on the outside. Q is a prime number, so phi of q is q take 1. The plain text, capital P, is relatively prime to q. So capital P to the power q take 1 is just 1. That, again, is our theorem on Euler's phi function. So I now have 1 to some power times p. Well, 1 to any power is just 1. And I get back to p modulo q. So that's almost what I want. I'm interested in showing that p to this power is going to get back to the original plain text, modulo n. And now this is true for both the prime factors p and q. So the thing we should be concerned about is, can we really glue these two congruences together and determine that this also holds modulo capital M? And the answer is yes. And this is where we are going to introduce our main theorem for this week. So this is the Chinese remainder theorem. The theorem states, if the greatest common divisor of two different integers is equal to 1, so if I have two integers which are relatively prime, then the system of congruences, x is congruent to a modulo p, x is congruent to b modulo q, has a unique solution modulo the integer p times q. So how does that apply for our current situation? We want a plain text which is congruent to our plain text to the power e times d. We know that the original plain text, capital P, is congruent to p to the power e times d modulo the prime factor p. We know that the plain text is congruent to the plain text to the power e times d modulo q. So in fact, the plain text is the only number that can satisfy those congruences in the integers modulo capital M. So in fact, we can glue together in this situation. And it's because of this GCD property. So we'll continue to talk about the RSA crypto system in this week's tutorial, and I'll be touching on some of the mathematics in tomorrow's lecture as well. The RSA crypto system is still used to this day. It was originally introduced in the 70s. But the practical version of RSA uses numbers which are far too large to work out by hand. The thing that makes this secure is the fact that we have a very large key space. So we are requiring computers to enact this encryption system for us. So for the rest of this lecture, I'm going to talk about the Chinese remainder theorem, which is a tool that we can actually use to solve congruences ourselves, either by hand or with a calculator. So this is material that will be appearing on next week's quiz. Let's take a system of congruences. I'm going to pick relatively small numbers for this demonstration. So I want an integer which has residue 1 modulo 4 and residue 2 modulo 5. In order to solve this system of congruences, I just need to follow 3 steps. And they will be the same 3 steps for any set of congruences like this. The first step is I want to find an inverse for 4 mod 5, and I want to find an inverse for 5 mod 4. Now these are very nice numbers because the inverse of 4 modulo 5 is just 4 again, because 4 times 4 is 16, which is 1 mod 5. The inverse for 5 modulo 4 is just 1, because 5 is already 1 mod 4. So step 1, find inverses. That's done. Step 2, I want to calculate 4 times its inverse and 5 times its inverse just as normal integers, so not using modular arithmetic. So I'll say I've got 16 corresponding to the modulus 4 and 5 corresponding to the modulus 5. And step 3, I can put everything together. I take the residue that I want, modulo 4, I multiply it by 5 and by the inverse of 5. I take the residue that I want, modulo 2, I multiply it by 4 and I multiply it by the inverse of 4, and then I take these numbers and add them up, which will give me my solution, mod 20. So I've got twice 16 plus 5, that'll be 37. And since I'm working in integers mod 20, that'll reduce to 17. And already I can check 17 is 1 mod 4, and 17 is also 2 mod 5. The thing that makes this work is that when I look at my formula, modulo 4, this bit drops out because 4 is 0 mod 4. And what I'm left with is the residue I want times 5 times the inverse of 5. The stuff in parentheses becomes 1 modulo 4, and I'm left with the residue 1 that I wanted to get. When I do the same formula mod 5, now this part vanishes because 5 is 0 mod 5. So this all is gone. I'm left with the residue that I want mod 5 times 4 times the inverse of 4. And I have a second typo here. This should be 4 times 4. We picked the 4 times 4 so that it becomes 1 modulo 5, leaving the remainder 2 that we wanted to get. We can also do this with more than 2 congruences as long as all of the moduli are relatively prime to each other. So let's take 3 congruences. I want to find an x which is 1 mod 2 and 2 mod 3 and 3 mod 5. The solution, I claim, is this formula. So we just have to calculate inverses for the numbers 15, 10, and 6. Those inverses will need to be calculated mod 2, mod 3, and mod 5. But I want to use modular arithmetic to find this inverse rather than division, because my final answer should be an integer. I do not want a fraction as the solution to this problem. Where did I get the 15, the 10, and the 6? Let's go through the steps again. So step 1, for every modulus n, so the 2, the 3, the 5, multiply all of the other moduli together and find the inverse of that product modulo that last modulus n that we picked out. So for 2, I take 3 times 5, which is 15. 15 is already 1 modulo 2, so 15 inverse is just 1. For the modulus 3, I take 2 times 5, which is 10. 10 is already 1 modulo 3, so 10 inverse is 1. For the modulus 5, I take 2 times 3, which is 6. 6 is already 1 modulo 5, so the inverse of 6 is just 1. Very nice numbers to play with. Step 2, multiply these products and their inverses that we calculated in step 1 just as ordinary integers. So here is my 15 times 1, which is the inverse of 15 mod 2. Here is my 10 times 1. 1 is the inverse of 10 mod 3. Here is my 6 times 1. 1 is the inverse of 5. 1 is the inverse of 6 mod 5. And for each of these moduli, take the residue you want, mod n, multiply it onto the product which does not have n as a factor. So this is my product that has no 2's in it. I wanted my x to be 1 mod 2, so I've multiplied these together. I wanted my x to be 2 mod 3. This is the product with no 3's in it. I wanted my x to be 3 mod 5. This is my product with no 5's in it. Put that together and I get 53 modulo 30. So my answer is going to be x must be 23, or any number that reduces to 23 mod 30. And again, I can play this same business with how do I know that I've got the correct residue mod 2? Because there's a 2 in 10 and there's a 2 in 6. Both of these residues drop away. Inside the parentheses is 1 mod 2, and I'm left with the residue I want. Why do I get a 2 mod 3? There is a 3 in 15. There is a 3 in 6. Both of these terms drop away. 10 by 1 is 1 mod 3, and I'm left with the residue I want, and so on. So these same steps will work for any number of congruences, but I need all of the moduli to be relatively prime in order to calculate those inverses. Those inverses will not exist if I have 2 or more moduli that share a prime factor. So this is the end of my lecture for today. I will write a similar lecture for tomorrow. Feel free to look this over multiple times at your leisure as needed. If you had any issue watching this lecture, either through the lecture recording on Echo 360 or through the video file I've posted to Moodle, please let me know so I can improve my online lectures for future classes. I plan to post sample quiz problems on Friday and solutions to those quiz problems the following Sunday. So we will still have a quiz. The quiz will be on Moodle instead of face-to-face. And I will also be working on sample test questions, as our midterm test is 2 weeks from Friday. That will be on 3 April. Thank you all for sticking through with this. I know that things are very uncertain now. No, I look forward to being able to see all of you again. Cheers.